begin today. In the first, I would like to thanks to the organizers about this very nice organized conference. So the Polish have polished everything. A very good way. So now, in my presentation, I will present experimental results together with part of the developed theory. I'm expecting a lot of questions, so the questions can be asked immediately after the presentation, or after that. I'm here until the morning of 31st of August. Anyway, critical temperature regard for experimental about cold diffusion reaction in constant time. A lot of actually questions, answers the questions can be found in this actually paper, which was published 2 years ago regarding Lerner experiments in solids. Sorry? Oh, I don't know. Okay. Anyway, the experimental scheme regarding replicable experiments with constant on wire about 300 degrees C and 400 degrees C, initial temperature of the whole specimen. So whole specimen contains actually constant on wire coiled on alumina rod. No plasma in the experiments has been used. Here we have optical spectrometer regarding determination of the initial temperature of the constant on wire of the whole specimen in these experiments. So now, 2 types of experiments were carried out. The upper one pertains to initial temperature 300 degrees C in interaction of constant time with nitrogen gas. Generally speaking, at 300 degrees C, we have gradually increased of the pressure of the nitrogen gas, and the initial temperature decreases because actually the incoming gas having room temperature used to cool the specimen. After the same experiments were repeated, the similar experiments were repeated at the initial temperature of the whole specimen, 400 degrees C. Again, we have gradually decrease of the temperature because the pressure of the incoming nitrogen increases. After that, we have repeated the same gradually increase of the pressure, and after gradually decrease of the pressure of nitrogen, where actually the temperature increases. Because actually nitrogen cools less with at low pressures the corresponding specimen. The same temperature, the same experiments were repeated in case of deuterium gas, exactly the same. Initial temperature 300 degrees, here initial temperature 400 degrees. As we're going to see, at certain point, after certain pressure, the temperature of the whole specimen increases here. After that, it decreases because of 2 reasons. One of them is the increase of the pressure of the incoming deuterium gas, which actually makes cooling better. And we are going out of the optimum pressure for which we can observe cold nuclear fusion reaction and energy decrease. So now, experiments with both nitrogen and they actually correspond to 300 degrees C of the whole specimen, which correspond 4 or 5 degrees C of the wire, and specimen initial temperature 400 corresponding to 524 degrees C of the wire, where temperatures are determined by optical spectral measurements applied to the Stefan-Boltzmann law. Now, again, I'm going to present only part of the corresponding theoretical explanation. Generally speaking, the model which I use is muonic molecule model, because actually the first law of nuclear fusion reaction has been observed in 1956, published in 1957 by Luis Alvarez and co-authors, and theoretical explanation is provided in a very good way in quantum mechanics, published in 1965 by the Prof. So now, we have actually, instead of muon here in the model, there is electron between two nucleons. In my case, we are going to consider two deuterons. So now, in order to get cold nuclear fusion reaction, we have to reach effective mass of the electron equal to the effective mass of the muon. So now, there are two ways this effective mass to be reached. One way is if we use known structures, which are engineered in order, by defects, this effective mass to be reached. The other way is, which is used in this case, is actually based on lattice vibrations, by using of second quantization in the quantum mechanics. Theoretical prediction using actually this formula. By the way, regarding this effective mass, I would like to say it has nothing to do with effective mass coming from the electron band structure. I'm talking about the electron effective mass pertaining to localization of the electron. These are the things. So now, this actually formula here, M0, and where M0 is the electron mass in rest, exponent, and certain expression. This formula provides opportunity that we have to increase the temperature in order to get cold nuclear fusion reaction. In case of constant time, based on lattice vibrations, experimental temperature was, critical temperature, was determined to be about 496 degrees C. Theoretical finding, however, using the formula below, is 510 degrees C. So now, in this case, the electron between two nucleons, two deuterons in this case, will attract both of them. It means the deuterons will not attract the heavy electron. The heavy electron will attract deuterons based on this actual temperature. There is a reasonable question based on the previous presentation. Is it possible cold nuclear fusion reaction to be observed at low temperature, let's say room temperature? Yes, it is possible. Because if we consider distribution of lattice vibrations versus the temperature, even at room temperature, we can get part of lattice vibration satisfying the conditions about getting of heavy electrons. However, this actually lattice vibrations, so the amounts of this lattice vibration is relatively low. In order to get significant cold nuclear fusion reaction, we must reach a corresponding temperature in order to proceed with this one here. Replicable experiments with the constant on wire of between 666 and 681 initial temperature of the wire. No plasma were used. By the way, in this case, the temperature of the whole specimen, including aluminum roller and wire, was measured in two ways, by barometer and by spectrometer, in order actually both temperatures to be distinguished. It's possible to be done. Okay, so now, there is actually plasma source here, we can see, but I don't use plasma source in the experiment. Simply, it is based on my existing reactor, chemical reactor in at my lab, so these are the things. So now, this is actually the reactor tube. The barometer is visible here. Here we have heating provided by AC voltage supply. Here we have view of the specimen, you see, inside of the reactor tube, through the window which can be seen here. Now, before interaction, again, we are not using plasma. Before interaction, we have this kind of view, which even visually we can determine that the temperature of the wire is between 650 and 700 degrees C. After the interaction, we can see the glow here, the rod is visible, which means its temperature is greater than 550. Here the rod is not visible. And the brightness of the wire can correspond even visually in the range about 1000 degrees C. Now, barometer temperature measure, we're going to see the video one. Barometer temperature measured initial temperature about 520 C. Corresponds to this is temperature of the entire specimen. It corresponds to the temperature of the wire 666 C. By using of Planck's law, it can be determined. Let's see the video now. Now we're going to see 2 minutes video clip presenting cold refrigeration reaction. In the beginning, we are going to see that the temperature will not increase. It comes from the fact that the incoming deuterium gas is cooling the entire specimen. After that, actually, due to energy release, the temperatures will go up. Let's start. Okay, I'm going to continue. Thank you. Okay, thank you very much. So now, initially you can see here something which is not exactly visible because of the lights here. It is, I'm going to show here how things are going. You can see here in the window a coil, which is again usually between 650 and 700 degrees C. Coil around which is not visible. Which is not visible. Because actually this temperature is below 550 degrees Celsius. Okay? Now, I'm going to begin the video clip. The brightness of light increases. And now we can see that the rod is visible and there is a glow around in the chamber. At a certain point of the time, we are going to stop the incoming deuterium gas. You see the glow in the chamber. In the meantime, by the way, I'm going to mention that actually the incoming, the excess energy is not based on, doesn't have electrical origin. The amount of the energy pertaining to, you see now it is visible, pertaining to chemical origin is about 700 times less than the total released energy. Okay? And I can explain why it doesn't pertain to some other things like distortion or deabsorption. Now, we're going to stop in 1 minute. Okay, the stops. We don't have injection of the cooling deuterium now in the chamber. We saw actually the maximum of the glow, the maximum of the brightness, and now the reaction goes down because there is no injection of deuterium in the chamber. Okay. That's it. We can stop now. And to return to the
have 5 minutes?
Okay, 5 minutes. I can do the previous presentation. That's okay, so now, as we're going to see, I don't see the pointer anyway here, but anyway. Oh, there's one. Okay, so now, we can see here the initial temperature. For 5 pulses here, in the experiments, we have excess of the temperature. Again, it is the temperature of the whole specimen. So now, including actually time when actually we have injection deuterium, let's say this pulse here, stopping of deuterium, and continuation of the reaction. So now, generally speaking, the release power is in this range, approximately 188, 189, up to approximately 209, 208 watts average power. The density of the average power is between 117, 118, and 130 watts per gram of the wire. Significant amplitude here. And the time for performance is between 30 and 31 seconds, approximately the same time. The temperature of the wire goes above 1000 degrees C. This is the view of the specimen after a lot of experiments. The experiments are replicable, and one of the specimen can be used for all of them. This actually here presents, if we increase the pressure, you can see here the power release decreases. It's important to be known. So now, release of helium-3 and helium-4. It is actually the cones in the histogram which I would like to say about helium-3, helium-4 deuterium, and helium hydride. It is actually the view if we have nitrogen deuterium gas and nitrogen dominance. I'm not going to spend attention. Now, release of helium-3. I use, in order to avoid the speculations, ratio between mass unit 3 and mass unit 4. Okay? Versus the energy release per deuterium pulse. As you can see, when energy release decreases, here we have the energy release in joules, the ratio here decreases too, which means that the mass unit number 3 decreases, and the mass number unit 4 we should expect to increase. It's regarding helium-3 release for different temperatures. So now, we can see here again, I'm going to explain the corresponding questions if there are any. We're having deuterium, heavy electron, deuterium, 2 heavy electrons, 2 protons, giving 3 helium, 2 electrons, and 2 protons plus energy, 1 proton plus energy. Again, I'm going to explain all these things later. About helium release. Helium-4 hydride versus mass unit number 4. We can see with the increase of the pressure, the energy release decreases, but the ratio helium-4, and mass unit number 5, mass number unit 4, decreases too, correlation to the energy. Again, we have actually reaction here, deuterium plus deuterium giving 4 helium, 2 heavy electrons plus energy. If we have 2 heavy electrons in the fusion well, which actually are doing streaming. Just actually comparison between the experiments at Lake University Lab and National Ignition Facilities Lab. Here, the ratio output power, input power at Lakehead is 3.9 for 100 for 16 integrated. Here is 1.54. The operational temperature is between 650 and 1012, 200 C. Here is greater than 3 million. Okay. Here we're using only deuterium gas. Here, deuterium-tritium gas mixture, tritium is radioactive. Release radiation, no radiation release, no reported data. The same is regarding radioactive waste. No reported data, no radioactive waste. Now, there is a theory, I can explain about this theory later, which in fact provides opportunity that we may have a neutron release, but the probability is very low. Gamma release, we shall not expect gamma release, based on this publication here. And the release energy comes from cold nuclear fusion reaction in the constant unspecified, caused by the absorbed deuterium. Thank you very much for your attention.
We have time for a few questions.
Thank you. Sorry. You were analyzing about the mass 3, helium-3, and you will have HHH, 3H, proton. How do you discriminate HHH and helium-3?
Could you please repeat again your question? Perhaps I cannot understand you right way.
HHH, proton produce a mass 3. Okay?
Proton.
Yeah, yes. So discrimination between HHH and helium-3 is very important to identify.
Yes, you mentioned this one here. I mentioned actually my question here. We can have actually 2 protons plus 1 proton can get actually helium-3. It is true. But actually, I didn't have time to explain. In fact, actually, the screening heavy electron changed the nature of the proton. It becomes neutron, Hg is stimulated.
Based on your theory, it would be possible.
It is possible, yes.
I'm asking about the measurement, the mass spectrometry.
Yes.
So, based on your data, you will, of course, helium-3 may exist, but HHH will be very important for mass spectrometry.
Molecules with 3 protons.
Yes, you see now, I agree that actually, again, it is possible you to use hydrogen. Heavy electrons, in fact, actually, to get helium-3 is possible. Okay?
It is according to your theory, but you know you have also neutron plus proton as a mass 3. It is also possible. So it is even much more possible than 3 protons. But this, I wanted to ask about your theory. So heavy electrons, you are arguing this something I call collection of many electrons that are put into, let's say, interacting crystals, something single crystal, okay, inside. So how you can imagine that you have maybe 400 electrons that should be put into one single crystal cell? It's not possible, okay?
Which is not possible?
400 electrons to put into 2 angstrom or 3 angstrom space, it is not possible. So the screening, or large amount of the screening, or large effective electron mass results from long distance interaction between electrons, not at very small distances. This is a collective effect. And therefore, if you are speaking about, high effective electron mass, this is the result of long distance interactions within the, let's say, crystals, solid state, something like this. There's not only one heavy electron, this is completely different.
Well, I'm going to explain these things here. You see now, in this case we have 2 heavy electrons in the well.
This is your picture, but reality is completely different. Heavy, heavy mass or large effective electron mass results from long distance interaction between electrons. There are many of electrons that can contribute to the collective behavior of the electron gas. I agree there are some materials that have even much higher effective electron mass than 200. But there are still completely different situations. There is not local system, there is large scale system. And this is one point. Another point, you are speaking about vibration of the lattice. And have you observed any temperature dependence of the effective electron mass?
Mm-hmm.
How?
In fact, well, I explained to you. Generally speaking, let me see now.
I am not speaking about the activity of your system, because effective electron mass can be measured independently without any nuclear reactions or missing electron. Electron effective mass can be measured optically using resistivity by different methods. So the question was, could you measure it independently, not because of your heat measurement?
Generally speaking, I think we are talking about different matter. Electron effective mass I used to explain in the very beginning of my presentation. This doesn't pertain to electron band structure, because electron band structure, I'm going to tell you why. The electron band structure can be used if we have ordered structure and if we have indeed electron function which is not localized. Here, in the theory which I propose now, the electron is localized, and we cannot use the theory regarding electron band diagram for definition. No, we cannot use.
Of course you can. You have, for instance,
oxygen. Okay.
Yeah, we can do it.
Local electrons are local electrons. The electron wave function is located in certain point. In this case, actually, here we have the corresponding well where the electron is localized. And this well, by the way, cannot accommodate. It may accommodate actually 2 electrons, 3, depending on the levels in the way. But for complete electrons, they cannot accommodate.
Localization of electrons, it means that you have a change of the electron band locally. It is something what we can measure, we can understand as well. So, but we can discuss it later.
We cannot use actually electron band structure theory.
I think we have to go to the next question because time is going quickly.
Thank you very much, Dimiter. Did you confirm your energy production by mass flow calorimetry?
Can you speak in English, please?
Did you confirm your excess heat by mass flow calorimetry?
Well, actually, in fact, actually, the released total energy is greater than the energy which I demonstrated here, because only on the change of the temperature, measured by barometer and after actually.
Okay, so that's my challenge. So yes. The challenge is that using a proton-rich oxyhydrogen gas in Japan, we were able to make indium, which melts at 156.6 degrees, turn to a jelly but not melt, but it glowed brighter than the sun. So you cannot lose the color temperature to assess temperature and therefore excess heat.
I don't understand your matter. Could you please repeat again?
Indium foil, 75 microns thick. We exposed to a high velocity jet of proton-rich gas from oxyhydrogen source, and it glowed brighter than the sun, but it did not melt. It turned to a jelly and flapped around like a piece of rubber, but it glowed incredibly brightly. So what I'm saying is, if you use the color temperature as a basis for your excess heat generation, I don't think it's reliable. So I think you need to use mass flow calorimetry.
Okay, I think we have to stop here. We can talk during lunch.
We can use
lunch is a good time to talk about this difficult subject.
In this case,
so, Dimiter, I think we have to stop here because they are waiting for us at the lunch. It's time for lunch at the ground level at the restaurant. Everybody is welcome there. If you have your badge on, whatever, something to identify yourself. Thank you very much for this session.